Thank you, Claire. Okay, so good afternoon, everyone, and many thanks for joining us online for this webinar. Also, thank you to the organisers for giving me the opportunity to talk about my work. Today, I'm going to be talking about the laboratory generation and also visualisation of internal solitary waves. So I'm going to start off with a bit of background and motivation. I'll then explain the experimental methodology before giving you some past examples, and I'm going to focus on work that's been published in JFM. And then I'll finish off with one slide, which will just talk through the current areas that are of interest to myself at the moment. Okay, so internal solitary waves are finite amplitude waves of permanent form, and they travel along density interfaces within stably stratified fluids. So one example of a stratified fluid is the ocean. So typically what happens around the world is that the sun comes out, it heats up the near surface waters, so they're warmer than the deeper waters, which tend to be colder and also saltier. So we get these two homogeneous layers of fluid, and between the two, we have a region where the density changes relatively quickly with depth. I'll refer to that as the pycnocline. And that pycnocline acts as a waveguide for internal wave motion in the same way as the interface between air and water acts as a waveguide for surface waves. Internal waves, however, have very different properties to surface waves. In particular, they can attain very large amplitudes. So for internal solitary waves, which is the focus of this talk, they can have amplitudes of up to 240 meters in the field. Okay, so they're very large structures within our oceans. They're of concern to the offshore engineering community, who want to know what kind of impacts and loads they have on things like cables, rigs and risers. They pose hazards to submariners, and they can also interfere with underwater communications. They're also of interest from a physical oceanographic perspective because they can transport mass and momentum within our oceans. They're important for ecology and biology within the water column as they're a source of deep water renewal. So that's particularly important for coral reefs. And in our polar oceans, we know that they can interact with sea ice as well. So lots of interesting applications and good reasons to study these waves. To generate these waves in the lab, I've got a wave flume at Newcastle. It's 7 meters long, 0.4 meters wide, and 0.6 meters deep. So we begin our experiments by filling with the bottom layer. So this is just homogeneous brine solution, and you can see it's being pumped into the flume. Once that's done, we have an array of sponges that float on the top of the water column, and we then very slowly drip feed fresher fluid from these two head reservoirs that sit above the tank. So if we want a sharp pycnocline, we just add on a fresh homogeneous layer directly, but we can also use something called the double bucket technique to give us a linearly stratified top layer as well. So once we've stratified the main section of the tank, we remove the sponges. We then have a gate that we put in at the upstream end of the tank. You can't see that in this video, it's out of shot. But what we do behind the gate is we fill with a different stratification in terms of the layer depth. So we typically put an excess layer of fluid behind the gate, which matches the top layer in terms of density. So that gives us a step in density across the gate. So when we remove the gate, due to the adjustment in buoyancy, we get a disturbance on the pycnocline, which propagates into the main section of the tank as an internal wave. So you'll have seen there Sam, my PhD student, he was playing about with some conductivity sensors that sit above the tank up here. They measure conductivity. As the salinity of the water changes, the conductivity readings change, and from that we can get the density field. You can also see that beneath the base of the tank, which is transparent, we've got a light sheet. So we make a thin vertical column of light, and we view from the side, and we've got our water seeded with neutrally buoyant light reflecting tracer particles. So you can see now here some output from the lab. So the top movie here shows you what we see with the naked eye in the lab. So we just see these white dots on a black background. So these are the neutrally buoyant tracer particles reflecting the light. In the middle panel, we're just seeing a false color scheme of that same movie. And we can often pick up a bit more detail by looking at this false color scheme. And in the bottom panel, we're looking at the output from PIV. Okay, so the vectors you see here represent the velocity field, and the color scheme is vorticity. And I use a software package called Digiflow, which has been developed by Stuart Diell in Cambridge to do my PIV analysis. Okay, so this first movie I'm going to show you, let me just pause it. You can see here what I've actually done is I've stitched 3 video camera outputs together. The bottom layer is just homogeneous brine solution, and you can see it's nicely seeded with these tracer particles. The top layer is fresh water, and this region here where you see the congregation of particles, this represents the density interface. So this is the pycnocline. These probes up here are those conductivity sensors I mentioned, and when I play this, you're just going to see a very large wave coming from the left, traveling to the right, and you can see that this wave actually breaks and it goes unstable, and we get these beautiful Kelvin-Helmholtz billows rolling up in the back of the wave. And if I let that play just once more, you'll see why that happens. What you'll notice if you look carefully is that the fluid above the pycnocline travels in the same direction as the wave, whereas below it goes in the opposite direction. So we've got a shear across the pycnocline, and if we push that shear high enough, we found that we were able to make these waves break in the lab. And for anyone who's interested in knowing more, this work dates back to 2009, and there was a more recent paper in 2017, both in GFM, if you'd like to see the details. So I've also looked at what happens when internal waves shoal. So in this case, what you're going to see, and this time the stratification is slightly different. We've got a linearly stratified top layer, and then we've got homogeneous fluid in the bottom. We're going to see a wave coming from the right. And if I just play this, here it comes. You'll see as this wave shoals, there's lots of really interesting fluid dynamics going on. If you look at the bottom boundary, we have some flow reversal. We have the generation of a very large vortex. That vortex causes the wave to collapse upon itself, and we can have this dense fluid propagating upstream. You can also see there's quite a bit of mixing going on there. The refractive index of the water changes, and the particles go blurry as a result. So in this particular study, we were looking at what effect stratification has on shoaling dynamics, and we found out that the stratification was very important. If you change the stratification, you change the kind of shoaling dynamics you had. And the example I've just shown there was an example of a collapsing wave. Again, if anyone wants to know more, this was also published in GFM back in 2022. I've also looked at mode 2 waves. So these are waves that displace isopycnals in 2 directions. So the prior examples I've shown you were mode 1 waves. Here's an example of a mode 2 wave. You're just going to see this wave hitting off the end wall of the tank and being reflected. At the top, we're looking at the output from the PIV. So the color scheme's vorticity. And again, vectors are given by arrows. You can see in this particular example, we had a second mode 2 wave in the wave train, and you can see the solitary behavior here. These 2 waves just pass through one another without changing their form. So we also looked at what happens when these mode 2 waves shoal. So in the first movie, you can see that we have a relatively shallow slope, and in the second movie, it's a little bit steeper. So in the shallow case, you can see we get this oscillatory tail associated with the shoaling wave. In the steeper case, there's no tail, but again, we see some very interesting boundary layer dynamics. We also see that the wave runs up the slope and it comes back down, and we get some reflected energy going back offshore. And this study was also in GFM, that was published in 2019. I first got into this field as a postdoc, and the main point of the postdoc was to try and measure the fluid beneath an internal solitary wave. So I just want to show you what we found there. So in this first movie, we're zoomed right in on the bed. The wave is traveling from left to right. You can see as the wave goes past, we induce a strong flow in the negative x direction. But then once the wave goes past and the flow decelerates, if you look closer, you should be able to see this boundary layer jet traveling in the same direction of the wave. So we actually showed that the formation of that jet was due to boundary layer separation in the adverse pressure gradient region. And you can also see that we got some resuspension associated with that prograde jet. We've also looked at what happens when internal waves interact with corrugated beds. So we've looked at depression waves and also elevation waves. Here I'm just showing you the example from an elevation wave. This wave was actually stable on approach, but due to the interaction with the topography, we saw this quite violent mixing and shear instability again associated with the interaction. We've also looked at narrow topography and broad topography. In this particular case, I'm showing an example of a mode 2 wave interacting with a narrow topographic slope. And again, there's some really interesting fluid dynamics that we've seen as a result of these waves interacting with the bottom topography. More recently, I've shifted focus to looking at the upper boundary, and in particular how internal waves interact with floating bodies in the context of sea ice. So 2 recent studies. One, we actually used real ice within the laboratory, and then more recently we used some weighted floats, and we've been looking at how internal waves transport sea ice and also how they interact with the underside of the sea ice. Unfortunately, don't have time to go into details. And just to very quickly finish off before we open up for questions, I currently have 2 projects which are active. One is funded through the Aura DTP. I've got students Dee Huang and Seth Sanderson. That's a collaboration with Rob Durrell and Charlie Lloyd in Loughborough. And we're looking at how internal waves interact with floating offshore wind structures, and also how stratified flow plast floating offshore wind structures mix the water column. And I've got a Leave Hume Trust grant with Ricardo Barros, Daniel Carter, Alex Doak, Paul Malwisky, and Niraj Prasad, where we're looking at the mathematical, numerical, and also physical generation of so-called multi-humped or exotic mode 2 waves. And with that, I will end. Thank you all very much for joining us and for your attention. Thank you.